In this section, we're going to, from the book, cover chapters 9 and 10, which involve talking about alkanes, alkenes, alkynes, and also cycloalkanes. So I'll be describing what those are. We'll talk about different conformations of these compounds and different geometries with them. But essentially what these structures are their hydrocarbons. So carbons and hydrogen attached to each other in different orientations and ways. And I'll talk about that in this chapter. So just to provide an overview of what those things mean, when we're talking about alkanes, you'll notice that ending ANES, that's just when we have carbons and hydrogens and only single bonds. Single bonds we also refer to as sigma bonds. Sometimes that's the Greek letter sigma. And when we're talking about alkenes and alkynes, then we're adding double or triple bonds, and these bonds are called pi bonds. So we always have the initial sigma bond, and then if we have one or two pi bonds, that means we have a double or triple bond. So those are referred to as alkenes and alkynes. Notice it's an A, E, or YNES ending. That's how we define those different types. And we're also going to look at arenes and different other types of cyclic compounds. So these arenes would be, this is a benzene ring where there's alternating double bonds. We can just have also cyclic compounds that are alkanes or just alkenes as well. So we'll also talk about some of those possibilities in this chapter as well. Just before we get into this too much, I want to kind of review some of the stuff that we had spoken about in earlier sections regarding the orientation of electrons, because this is going to really define what's happening with these alkanes, alkenes, and alkynes. And one thing that I didn't really get into was kind of how these things orient themselves around the element. So we did talk about the Vesper model, but it kind of doesn't really work with when we're talking about the shapes of the orbitals that we discussed with the spherical shape and the pin shape. And with the spherical shape, we have one orbital that can hold 2 electrons. And then the pin shape, we have 3 different orientations, which can each hold 2. But this doesn't really make sense because then it looks like we really only have 2 or 3 spots where we could bind another element and share electrons. So if we're looking at carbon specifically, we're looking at the electron configuration of carbon. We have the s orbital, which is in the middle. That first number kind of tells you what the size of that shell is. And then when we go down here, you notice we start adding the 2 shell. So 2, so it's a bigger shell and it's a spherical shape. And that's showing you right here those electrons. I'm kind of disregarding the inner electrons. I'm just looking at the valence electrons, which are the electrons in the outside of the element. So we start with a 2s1, 2s2. So these are the 2 electrons here. And then as we build our atom up, we get into a p orbital. So we have one that would be the same electron configuration for boron. And then we add another one for carbon because it has 2 electrons in that p orbital. So this other third p orbital theoretically is empty, and then it has 2 slots for binding other electrons. So how does this work? If we're looking at these 4 atomic orbitals in the valence shell, what actually we think is happening based off of chemical assays and different experimental things that have been found by chemists is that these are actually hybridizing into 4 different orbitals. So these 4 orbitals, they're electromagnetic radiation. They're wave functions. And waves actually can have interference with each other. So that's always the concern when they put up, for example, the 5G network for cell phones. There was a big concern once they did that the radio frequencies that are being transmitted through the cell phone signals are going to interfere with airplane signals, because that frequency is close. So there was a concern that there would be interference and that would ruin the ability for airplanes, for example, to communicate with each other. But this is the same idea. These 4, since they're in that kind of same shell and in the same space, they actually interact with each other and they have interference. And the interference changes the wave function. And instead of having these 4 separate ones with S has a spherical shape and we have 3 pins, they're kind of a combination of all of them at the same time. And what that also does is it allows us to separate these out because they have the same energy level. This is demonstrating energy. So a lower energy and a higher energy. When they hybridize, they all have a similar energy. And it allows us to split these electrons out more like how we looked at the VSEPR model, the valence shell electron repulsion. So these 4 electrons can split up evenly in a tetrahedral shape around our element. So here, let's look at this visually. This is the 2s orbital. It would be a sphere shape. And then we have the px, y, and z plane. And these would be the 4 atomic orbitals. Our hybrid orbitals would be sp3, which is saying we have 1 s orbital and 3 p orbitals that are hybridized into these 4 different orbitals. And you can see that they're oriented in a tetrahedral shape. So these are all kind of combined here. And this is where we now expect our electrons to be. So when we're looking at these compounds, this is kind of how this all fits together. And you will hear me describing these as sp3 hybrid orbitals, or I'll talk about sp2, sp. So sometimes they'll pull some of these out in order to make these double bonds. So in order to have a double bond, you can only hybridize 2 of these p orbitals. So you'd have an sp2. If you have a triple bond, you can only hybridize the s and p orbitals. So I'll talk about that. I just wanted to introduce you to that idea. It's not in the book very much, kind of like glosses over that, but I just wanted to introduce you to that so that you know if I mention it, that's what that means. So when we're bonding to these things, if we have a carbon in the middle and it's got sp3 hybrid orbitals, so it has 4 different orbitals and they're called sp3 hybrid orbitals, they're going to bond in this tetrahedral shape with 109.5 geometry, as we talked about within the VSEPR section. I know we're focusing on carbons here, but just kind of to review that idea with nitrogen and oxygen, because those are other elements that we're going to see throughout the semester. These do the same thing, and except for some of the orbitals that are sp3 hybridized just have lone pairs of electrons that are not being shared. So this also matches up with our valence shell electron repulsion theory. These ideas of hybridization kind of meld these ideas together. And as we talk about conformations, these things are going to be important in terms of the geometry. And again, just to review, if it's sp3 hybridized, this superscript really means that it's an inferred one here. So we have 1 s orbital and 3 p orbitals in this hybrid orbital. If we have sp2 hybrid orbitals, that means that we have 3 of these orbitals hybridizing, which means 1s and 2p, and we have 3 of those. So whenever you have a certain amount, so this is just showing you the sp2 hybrid orbitals, and we're not hybridizing this p orbital, which is going to be required for this pi bond that we're going to talk about. We can also have sp orbitals, which hybridize just 2 of these orbitals, the s and the p, and then we have 2 unhybridized orbitals. So again, just kind of to overview that idea and that concept, we'll come back to this when we talk about alkenes and alkynes. So we'll start with alkanes, and these have a generic formula for an alkane is a certain number, right? You have a certain whole number of carbons, and for every carbon you have 2n plus 2 hydrogens. So we'll look at that. So that's basically, this just gives you a generic formula for this so you can recognize if it is an alkane versus an alkene or alkyne. Not something you have to memorize, but just kind of giving you the idea. That just means that this carbon just has only single bonds associated with it and all of the elements that are attached to that compound. All of these are single bonds and they all have a tetrahedral shape. So we get the 109.5 degree bond angles. Alkanes can have different forms. They can be linear, so they just kind of carbon, 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 carbon. And just so you're aware, when we do this shorthand for writing out compounds, every end and every corner represents a carbon. So in this example here, if we're going to be looking at this compound on the top, this actually means carbon, 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 carbon. And it has the necessary hydrogens attached to it to give that compound an octet. So I'm drawing out all of the hydrogens, all of the carbons, but this top and the bottom structures are the same exact thing here. So this compound that's drawn below is the exact same thing that I drew in red. So it just has, you can see 1, 2, 3, 4, 5 carbons. We have 1, 2, 3, 4, 5 carbons. Those are the same thing. So you'll see this shorthand that's called a skeletal structure, and you'll have to be able to distinguish between a skeletal structure and kind of these written out Lewis structures. They mean the same thing. So we can draw these as straight chains. We can also have branched chains, and we have carbons at each of the corners and carbons at the ends and the corners. And we can start to think about this idea of isomers. So if I have a 4-carbon chain, so I'll start with 1, 2, 3, 4. I can change this to be another different type of 4-carbon group. 1, 2, 3, 4. So you'll notice I came out of that third bond is coming out of the center carbon. So we can have 2 different conformations. These are not the same molecule because one is linear and one is branched. And these are isomers because the compound still has 4 carbons. And then if we would count the hydrogens off, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's H10. And for the bottom molecule, I'm going to just draw these out with red dashes to kind of indicate where the hydrogens would be. Of 3 on the end, 1, 2, 3. And then we'll have 1 in the middle, 3 off of this chain, and then 3 off of the end. So you'll notice a pattern here. When we're on the ends, we'll have 3. When we're in the middle, you'll have generally 2 things attached, right, to the middle carbon outside of that chain. And then on the top, again, we have 3 and 3. So we have 9 and then 10, so that the same structure. And you can just kind of check again, carbons should be attached to 4 things. So if I'm on the end here, I have 1 attachment to another carbon. That means I have to have 4 other things that I'm attached to. And this is where we talk about hydrocarbons. So the hydro part is the hydrogen. So we're assuming that all of these carbons have the appropriate hydrogens to give that compound an octet of electrons in their valence shell. So the longer the chain of carbons, so we have this 1 carbon, 2, 3, 4, 5, 6, 7, 8, 9 to 30. The longer that carbon chain, the more different types of isomers or different orientations we can make. So we can quickly make a lot of different orientations and combinations of carbon once we get up to 30 carbons, for example. That means that we have to have a different way to distinguish these. And we actually have different ways of naming all of these. There are specific ways, and we're not going to go through all of them, and we're not going to do this right now, but you're welcome to look at some of the rules. We're also going to talk about functional groups, and we're not there yet. But when we talk about oxygen and nitrogen and different types of halogens being attached, we have different ways to name those as well. So to be very specific, we don't want them to be ambiguous, right? They should be unambiguous names. So I can give you a name of a compound and you can know exactly which isomer it's going to be and exactly how to draw that out based off of the name. So that's the point of nomenclature for organic chemistry. We're not going to go through all of that. We're just going to do some simple molecules for this class. Where we're going to start is basically just looking at the length of straight chains for now. And we're looking at this, if we have 1 carbon, there is a base name that we have for defining that carbon. So if we have 1 carbon, it's a methyl group or a methane. We have 2, it's an ethane, 3, propane, 4, butane, 5, pentane, 6, hexane, 7, heptane, 8 is octane, 9, nonane, and 10 is decane. So we can go through, and if we have a 8-chain carbon group, we know that's an octane group. So this is the way that we name these things. For some general ideas of naming, if we put the ANE, means it's all single bonds, and it means that all of the carbon atoms are saturated with hydrogen. If we use the YL ending, that means that, so if it might be something like methyl pentane. Pentane is the longest chain group, and then this methyl group, this shorter group, you'll see this YL suffix. That means it's attached to a longer group. So 3-methylpentane would, for example, look like this. We have a methyl, ethyl, propyl, butyl, pentyl. So that's a 1, 2, 3, 4, 5 carbon group. That's my pentane. They're all singly bonded. And then on the third carbon, I'm going to actually attach, and I'm going to just draw it through there, I'm going to attach a methyl group. That's 1 carbon, methyl. So this is how the structure for 3-methylpentane would look like. And that's kind of that general idea of organic compound naming. Cyclocompounds, cyclopentane means that's cyclic, so it's in a circle. So we'd have 5 groups, 1, 2, 3, 4, 5 carbons, and they're all attached in a ring. So that would be cyclopentane. Then we can also we'll start to look at adding some halogens. Fluorine, chlorine, bromine, iodine, those are all going to be based off of where it is on that carbon if we have a cyclopentane. So again, we have this ring structure with 5 carbons in it, and we're going to have fluorine on one of those. So that would be 1-fluorocyclopentane. So just an idea of that naming structure, and we're not going to get into naming too much, but I just wanted to give you a little bit of an understanding of how those things are named, and just to look at some simple examples there. So why does it matter what's in that name? Some of the names you'll probably have recognized before. Methane, propane, butane, those are all things that you might use in your propane tanks to have your grill. Butane lighters are common. Methane is what we use a lot of times for heating fuels. So these things are going to be based off of their size, and you've probably heard of octane in your gas tank. A lot of cars run on different types of octane levels, and you're looking at 8 different carbon groups. And so that is kind of the difference here. We're looking at different lengths of carbon, and we're looking at gases or petroleum for cars, different types of chemicals we use in chemical synthesis. Jet fuel gets a little longer, diesel fuel gets a little longer. Then we start looking at waxes and oils, different types of ships or asphalt. So we'll use these different components for different products. Smaller molecules, smaller elements, you'll notice these are gases, and then we get down to oils, and these are going to have different characteristics and properties. So this is what refineries do. They take crude oil and they'll go through this process of distillation where they'll heat it up and it'll refract and it'll come out at different temperatures. And so very early on, what happens is the things that have really low boiling points, those will come out right away, and you'll be able to isolate those and separate those out from all of these other things. And then we can use those things as we separate them out by fractioning them off in these different spots. So here's a nice little graph that just kind of looks at the number of carbons on the bottom. So we go from 1 carbon to 14 carbons. And then we're looking at the melting and boiling points. So the melting points in blue, boiling points in red of these. And you can see that based off of the number of carbons that we have an increase as we increase the number of carbons for both the melting points and also the boiling points as well. So this is just kind of natural gases over here. Then we get to gasoline, then we get to kerosene and gas oil, for example. This is the same idea and concept that's used for distilling alcohol. When you make large amounts of alcohol, then you're also using kind of those boiling points and those different temperatures to pull out different components. So this is just kind of looking at some of what the concentrations of various compounds, and we're not going to go into great detail about this, but I just kind of wanted to kind of show you that you can do multiple distillations. And a lot of times you'll talk about the heads versus the tail versus the heart. the heads are typically going to be things that you don't want to have. So those are the things that are coming off first. So if we look at this analogy of kind of the bottled gas, the methyl group, the difference with alcohol is it has an alcohol functional group on there. So you've heard of methanol. Well, methanol is poisonous. It will potentially make you go blind or die. So you don't want to, this is why distillation is regulated, because if someone's not very good at it, you might get high levels of methanol, for example. You can see methanol here in the first distillation is about 14%. That is not going to be really something you want to consume. In the second distillation, this head still has about 60 milligrams per 100 milliliters of that methanol in it. So we want to get rid of those things, and you have to be careful with methanol in your alcohol. The tails aren't necessarily bad for you. Those are kind of, we can come back here, right? The heads would be up here, really small things like methane, remember, but then we're just adding the OL ending, which is methanol. If we have longer things, those just tend to kind of taste oily and not really be very good tasting. I don't know if you've ever heard of Malort's. It's an awful tasting liquor that's kind of used as a joke. If you don't like someone, you give them a shot of this. I think it's because I think I've had it before. It tastes like it's almost entirely the tail end of a distillation process. It tastes awful. But I think there's a lot of off flavors in there. But just to kind of relate this to distillation, this is the same idea is done for gases that we use to just these standard fuels here. So the same concepts, just using it for distilling alcohols instead of just normal straight chain carbons. And the length and the shape do determine that different types of boiling points, and it's because of the intermolecular forces that are allowed. So if we have a long chain of carbon, like pentane shown here, 1 methyl, ethyl, propyl, butyl, pentyl, right, pentane, we can see kind of on this little cartoon drawing how these can stack up. But if we have a different isomer, so we have still 1, 2, 3, 4, 5 carbons, but they're oriented differently. So we have this tetrahedral shape around the central carbon. These can't stack on each other as well. So you can see the difference in the boiling point is 10 versus 36. And this has to do with the van der Waals or London dispersion forces that we've spoken about, where you have these temporary induced dipoles where they have these attractive forces. So you can get these, the longer the chains are, they can fit on each other better. But as we have branched chains, those break those interactions up a little bit. So as we look at, we only have those intermolecular forces that are called the van der Waals or the London dispersion forces. That's all we have for hydrocarbons. But as we increase the number of carbons on the atom, which is shown here in the X, and look at the boiling point, we can see that the shorter the groups, they become liquids as they become longer because they have more of those interactions. And as we add more chains, that also decreases the boiling point because it decreases the intermolecular forces that are happening. Something else that's related to the intermolecular forces are when we have big long chains of carbon like this, they're not going to be very soluble with water, for example. If we look at the structure of water, H2O, or this is an R for just an organic compound like an alcohol that also has the OH group on it, we have these hydrogen bonding that can have interactions. However, when we have these long hydrocarbons, there are no positive or negative charges that are kind of created through these bonds. So a lot of the things like vitamin A, vitamin E, these are not water soluble. They're fat soluble, but they're not going to want to interact with water. Where vitamin C here, you can see there's a lot of OH groups that will be able to be attracted to these types of hydrogen bonding situations. So this is the idea of like compounds dissolve like compounds. So water would dissolve vitamin C. It's very water soluble, but vitamin A and vitamin E, as examples here, long chains of hydrocarbons, those are not water soluble. I also want to talk about ring structures as well. These are also hydrocarbons, and this is an example of a cyclopropane, so methyl, ethyl, propyl. So there's 3 carbons. You can see that this ring is a 60-degree bond angle. And the normal happy bond angles around 109.5, excuse me, for a tetrahedron, right, with 4 things attached, 109.5 is ideal. That means that this 60-degree bond angle is very strained. And those are very reactive chemicals, these cyclopropanes, for example. Pyrethrin from the chrysanthemum is actually a potent insecticide. So you'll notice that these flowers typically don't get eaten by very many things, and that's because it has this chemical structure formula in it, and it's got this 3-carbon ring that's very reactive. So it's a potent insecticide. It'll target the nervous system of insects if they do eat this. So generally they stay away from these. These are also, the pyrethrin is synthesized industrially, and it usually, it also occurs naturally in these flowers. There are other types of rings. We can have cyclobutane, so methyl ethyl propyl butyl, so where we have 4, and sometimes they're drawn out with kind of like the show that it's not really flat because of the bond angles are about 90 degrees, but they tend to kind of pucker in their conformation. What do you think here in terms of 90-degree bond angles? Do you think this would be more or less reactive than linear butane? And I'd like you to answer that question in our Blackboard space. Interestingly, some place where cyclobutane can occur is with UV damage to our DNA. So that's why it's recommended that we wear sunscreen to help us getting from skin cancer. What can happen is that we can have enough energy that will allow chemical bonds between sugars in our DNA to break apart and reform in these cyclobutanes. These can be replaced and fixed in our bodies with our DNA excision and repair mechanisms. But this is kind of one of the mechanisms that's thought to lead to skin cancer if this doesn't get fixed and repaired, for example. Here we move to a larger ring, methyl ethyl propyl butyl pent. So cyclopentane, those are the examples I gave you before. And we typically draw them out like this. If you're looking to draw it as if it's kind of 3-dimensionally what it would look like, more of like an envelope sort of, that's kind of the best way to represent this in 3-dimensionally. Typically, we just will draw it out like this or like this just to show how it's organized in space so we can attach things to it. 105 degrees, less strained. These are commonly found in biological compounds. And finally, we're going to look at the cyclohexane, where we have 1, 2, 3, 4, 5, 6. More often, we're going to draw it without all the hydrogens because the hydrogens just kind of make it kind of more complicated than it needs to be. So typically, you'll see it drawn out like this. Very common in nature. It also has 109.5 degree bond angles, so it has the normal set of groups or the normal bond angles, so it's not that strained. The only difference is that you're kind of stuck with the different orientations of the compounds. We can't roll these over and kind of spin these around. You can't kind of have free rotation around this whole thing. So you're kind of stuck with these compounds with various conformations. So we call this a chair conformation, where we have different groups in an axial position on the top and the bottom versus equatorial positions. And the kind of a vocab here is axial is just like the axes of a car tire, and then the equator on the outside. So these just point out different ways, and they're going to change some of the chemistry and the chemical reactivity of these different groups. We're not going to focus too much on those right now, but I just wanted to introduce that to you. And I also just want to show you this figure where this is the freedom of motion it has. We can move some of the axial to the equatorial. So this A is in red. This group can kind of switch down to the equatorial plane. So we can switch all of these around, but that's it. We can't kind of rotate through the middle. These, like this equatorial hydrogen, can't come through the middle of this ring and come back up. It can kind of just flop back and forth. That's kind of what we can do in terms of the movement. So there's a little bit of restriction in the movement, but they're still really stable compounds. When we're talking about chemical reactivity, they're not very reactive, these long hydrocarbons. in terms of, unless you're talking about a cyclopentane, for example, just because it's so strained. But they're not generally going to interact with acids or bases. They're not going to have redox reactions. And this is beneficial for biological systems because then we can have groups of these that surround an environment, for example. So we have our fatty acid lipid membrane. They're not very chemically reactive, so they can keep chemicals in and out. We can package them and organize them and have them be separate from the rest of our environment. So these are kind of the backbone for the functional groups that are actually going to have biological functions. These are also really good solvents, so we can use those to kind of have chemicals react that do have some of these acid or base compounds. And that's kind of the next section. We'll talk about acids and bases. But some of these backbone parts are not going to react with acids and bases. One type of chemical reaction that we can get to happen with these different types of alkanes is this halogenation. And one term I want to show you, or one idea, is that if you have an R group in organic chemistry, R just means that it's a organic compound. So it's a hydrocarbon, for example, a group or a chain of carbons. And it's going to, with one of the hydrogens on there, it could be anywhere, it's going to release that. So we're going to be looking at a substitution reaction. And we essentially have, and I'll just draw kind of like an example below, maybe we have methane. And we have a CH, H, and H, and this is the hydrogen that's going to interact. And then we'll have maybe chlorine and a chlorine attached. So that's the X. The X is a chlorine or a bromine, for example. With heat or light, we're able to break this bond, and then that interaction, we're going to kind of do a swapping of that hydrogen and that chlorine. So you can see that's what's happening up here. We have this group. It would look something like this now. And then we have our hydrogen and our chlorine that's left over. So this is a way that we can attach halogens, and halogenation is that other type of compound that we wanted to discuss in this chapter. So it can be chlorination or bromination. Those are different ways that we can do that. So that's where I'd like to stop here with the alkanes and cycloalkanes, and I'll get into the alkenes and alkynes in the next lecture.